Hey everyone, welcome to The Explainer. Today we're mapping out two of the absolute foundational forces of chemistry, electron affinity and electronegativity. We're talking about the invisible tug of war happening right down at the atomic level. It literally dictates how all matter interacts. Why some atoms greedily hoard electrons while others just kind of let them slip away. Okay, let's dive right into this. Here's our exact roadmap. 1. Defining electron affinity. 2. Electron affinity variations. 3. Defining electronegativity. 4. Electronegativity and bond types. And finally, 5. Electronegativity variations. All right, starting off with section 1, defining electron affinity. So what exactly is electron affinity, or EA? Simply put, it's the measure of the energy change that occurs when an electron is added to an isolated gaseous atom. I want you to think of it kind of like a transaction. A stray electron docks with a solitary atom's electron cloud and an energy shift happens. That specific shift is exactly what we're measuring here. And when this initial process happens, when that first electron successfully docks with the atom, energy is actually released or given off to the surrounding environment. So it's an exothermic process. To be precise with our math, we track this specific energy exchange in units called kilojoules per mole, or kilojoules per mole. This basically gives us a standardized way to compare how eager different elements are to accept an extra electron. Now, what's really fascinating is what happens when we try to add a second electron. The first electron affinity usually releases energy, but the second electron affinity, that is always a positive value, meaning energy is suddenly required. Why? Well, once the atom has gained that first electron, it becomes a negatively charged ion. Like charges repel, right? So forcing a second negative electron into that already negative system takes a massive amount of energy. Moving right along to section 2, electron affinity variations. So the crucial point here is how space and distance dictate this atomic behavior. Generally speaking, as you move across a period, from left to right on the periodic table, electron affinity increases. This is because the overall atomic size decreases. Those smaller atoms have their positive nucleus closer to the edge, so they grab that incoming electron much tighter. Conversely, as you move down a group, top to bottom, electron affinity decreases. The atoms are getting physically larger. They're adding more electron shells, so that positive pull from the nucleus has a much, much weaker hold on an incoming electron. All right, section 3, defining electronegativity. Let's see how this builds. We are transitioning now from isolated atoms to atoms in an actual relationship. Electronegativity, or EN, is the ability of an atom to pull or attract a shared pair of electrons to itself in a covalent bond. I really want to emphasize those words for a second. Pull, attract, and shared pair. While electron affinity was about one atom taking on a totally new electron from the outside, electronegativity is a literal tug of war over electrons that are already being shared between two bonded atoms. It's definitely worth pausing for a brief historical nod here, because we gotta give credit where it's due. This incredibly elegant framework was first put forward by the legendary chemist Linus Pauling. He's the one who gave us the scale that lets us quantify this atomic tug-of-war, which completely revolutionized how we understand chemical bonding. The rule of thumb here is super straightforward but extremely powerful. If an atom has a high electronegativity value, it has a strong pull, and it tends to attract those shared electrons closer to itself. On the flip side, if an atom has a low electronegativity value, it essentially loses that tug of war, and its electrons are pulled away toward the more electronegative partner. So who are the reigning heavyweights of this tug of war? Here's your podium. Number 1, the absolute undefeated champion is fluorine. Number 2 is oxygen. And number 3 is chlorine. Basically, if you ever see fluorine, oxygen, or chlorine in a molecule, just know for sure they are aggressively hoarding the shared electrons. Which brings us to Section 4, Electronegativity and Bond Types. And this slide brilliantly illustrates exactly where Pauling's math shines. You just subtract the smaller electronegativity value from the larger one. Is the difference greater than 1.7? Then the stronger atom steals the electron entirely, giving you an ionic bond. Is it between 0.4 and 1.7? Well, they share, but unequally, making a polar covalent bond. And if it's less than 0.4, it's a fair fight, shared equally, resulting in a nonpolar covalent bond. Finally, Section 5, Electronegativity Variations. Notice the beautiful structural repetition here. Just like electron affinity, electronegativity increases as you move across a period from left to right. Again, this is because of the increased nuclear charge and the smaller atomic size pulling tightly on those shared electrons. And similarly, it decreases as you move down a group. As the atoms get physically larger with more electron shells, the nucleus is just too far away from the shared pair to exert a really strong pull. The trends perfectly mirror one another, which is exactly what makes the periodic table such an incredible cheat sheet. To wrap up, I want to leave you with this final thought. We've spent this time mapping out the math and the periodic trends of how atoms hoard or share electrons. But think about this. If these invisible, microscopic tugs of war dictate whether a bond is ionic, polar, or nonpolar, how do those differences in electronegativity shape the physical properties of literally everything around us? Think about it. It's the exact reason water dissolves salt, the reason oil and water don't mix, and the reason our very DNA holds together. It all starts with the simple tug of war we outlined today. Keep that in mind next time you look at the physical world. Thanks for joining me on this explainer.